Hello. This video is entitled Conservative Vector Fields and Independence of Path, and let's talk about what that means. So if we're evaluating work, which is the line integral of the vector field dotted with the derivative of the path c that it's taking, and this is an interesting little statement here, that the work done by a conservative vector field, which we've learned what that was before, is independent of path. And what that means is, and I just kind of drew out 4 examples here. Let's say, and these are supposed to be the same starting and finishing points. That's the whole idea here. They're the same points there, the black dots. And you can parameterize this any way you want, and it would produce the same amount of work. Now, the last two here, this C3 and C4, are kind of silly because, I mean, nobody's going to do it that way. But the point is, you could do it that way. C3 is really crazy because it's, you'd have to do all those individual paths and add them up. So that would not be good. So obviously one of these first two would make a lot more sense. All right. Anyway. So if you have, going between 2 points and it does not give you the parameterization for the curve, you can create it any way you want. Now, from this problem in a previous section, we want to find the work done by the force field along the given path. So we had this problem earlier that we did as a line integral. So we're going to figure out the work that it does along that path. So I just have to get from 2, 0 to negative 2, 0 in any way that I see fit. And we're still using the fact that the curved path's coming around here. Well, I'm going to use a straight line. I think that's easy enough. I could even follow along that curve if I wanted to. I don't need to. But that's the point is, that's the curve C. That would work if I used that same parameterization that I would have used back when we did this problem before. In fact, let me see. I think I have that section up here. And so let me scroll back up in my notes. Yeah, there it was. Now this one, so there, we had to use that parameterization because we were specifically taking that curve. But we don't have to now. We could take it again, but we don't have to. Any path we want, I'm going to make it a straight line path. So as I go to the left, and it's horizontal on the x-axis, so y would always be 0. And then when I showed that one example, I believe in the first section on vector fields, that if you're trying to parameterize something like this and linearly, and if it goes to the left or down, it's going to have a negative in front of that t. So it's going to be a negative t, something minus t. So I just have to figure out, all right, I know I'm starting at 2 zeros, my first point. So if I go from 0 to 4, so obviously you can play around with the numbers till you get it to work right. If I put 0, I need this to be a 2 because 2 minus 0 right there gives me this 2 here. And then when you put 4 in there, 2 minus 4 would give you that negative 2. So that's a correct parameterization for that straight line. All right. And then the r prime, which is the dr, and the f dot dr is r prime, is negative 1, 0. Now here's our vector field, negative y, negative x. We don't really need the m and n thing here. This is just verifying that it's conservative. So that's why that was the only reason that was important, because obviously everything I'm doing here would be completely wrong if it wasn't conservative. All right. So now we have we substitute. We already have r prime right here. There's your dr right there. So this is the f dot dr. So we have negative y, negative x. I go right back up here. Well, negative y will just be 0, and the negative of 2 minus t would just be t minus 2. So I do the dot product. Well, this one happened to be 0, so I guess that kind of took the fun out of this problem because there's no integration to do here, so I wouldn't count on that happening too often. But so there's no need to integrate. So essentially, because there's no, this case, there's just no work being done. But I'm sure we can find something that where it won't be 0, and I think this next example will take care of that for us. We're going to find the work done by the vector field 15x squared y squared I plus 10x cubed yj. Now let's check to see that it's conservative. Now, you know, one thing, if it wasn't conservative, it would probably have to tell you the path, like it would say on the line or on the parabola or something like that. It's kind of giving a hint that it's conservative here because it's not telling you which way to go. Otherwise, you know, if it wasn't conservative, we would have to know specifically the path. So you do the my partial right here is 30x squared y. The nx is 30x squared y. It's conservative. So I can choose. All right, looks like I decided to have some fun with this. I don't necessarily have to work out all three of these. That's pretty crazy there, but looks like I just three ways. Just wanted to look at something. I saw something smudge there. I would probably do this the linear way if I was going to pick one, but I went ahead and showed. So I said let y equals 3x. That's a good one. From 0, 0 to 3, 9, right? You go from 0 to 3. Yeah, it gets you from 0, 0 to 3, 9. And then, so your parameterization, you let x equals t, y would be 3t. So you have this. And we have the derivative, dr, would be then 1, 3. So that's a pretty easy path there. So let's look at the next one. I said, okay, what if we chose a parabola? T comma y equals x squared, so it'd be t comma t squared, also from 0 to 3. And then the derivative of r here, right here, would be 1 comma 2t. And then I said, what if I went this way? X equals the square root of y. That would work, but it would be a different t. You'd go from 0 to 9, because that way the t goes 9 here. So you would say that y equals t, and then x would be the square root of t. So when you put 0 in there, you get 0, 0. And then when you put 9 in here, you get the square root of 9, comma 9, which will be 3, 9. But you don't have to do this three different ways. I'll probably just maybe look at the first two in detail. If it's in the notes, I'll leave it there, but there's probably no point in actually going through all the steps. But the idea is, because it's conservative, these paths will produce the same answer. That's what's key here. They should all be equal. So now I have to take this f up here, the vector field, which, let's see if I've got this copied down anywhere. Well, I've got, okay, I wrote it right here. That's good. So I'm going to copy that down. So there's the two components of the vector field. And of course, for this one, I'm putting a t everywhere I see an x and a 3t everywhere I see a y. So that's not too bad. Put it in both of those and just kind of tidy up the t's a little bit. So I get 15 times 9, 135 t to the fourth. And here I'll have 10 times 3, and t cubed times t. So I have 30 t to the fourth. So now I'll do f dot dr, which I've labeled with the subscript 1, meaning for the first one. Normally you wouldn't need that. If you were only doing it one way, you would not need it. So I'm going to dot this vector field now as a function of t with 1 comma 3. And I get 225 t to the fourth. Which means I'm going to integrate that from 0 to 3. That's what t is. So integrate that from 0 to 3, which you could use the numerical integration capabilities of your calculator to do it. But this one's not too difficult. So it ends up, the antiderivative ends up being 45 t to the fifth, because 225 divided by 5 is 45. Put in 3, put in 0. 45 times 243 is 10935. Now, path 2. So let me copy these down here again. I think I'll walk through this one and then maybe just not worry about the third one. I'll just kind of point at it and show you. Of course, I guess you can't see the, we still have to scroll up to see the parameterization. Well, no, there it is right there, t comma t squared. Okay, so I have it written right over here so we can see it. So this one we have our dr is going to be 1 comma 2t. That's our dr1, dr2, excuse me. And then so let's substitute. I'm putting in t for x, and now I'm putting in t squared for y instead of 3t. So you substitute this in there, you get 15t to the 6th, and then you're going to get 10t to the 5th. We're going to dot that with 1 comma 2t, and we'll get 15t to the 6th plus 20t to the 6th. That'll give me 35t to the 6th, which I will also integrate from 0 to 3. That'll give me just t to the 7 over 7. 35 divided by 7 is 5. 5t to the 7th. 3 to 0. 5 times 3 to the 7th. Boom. 10,935. Same answer as the first one. Okay, this one just kind of yielded some fractional exponents. But like I said, this would not be a route that you would probably choose anyway. Why put a square root in there if you don't have to? But anyway, I'm going to skip this one, but it's, it's there for you to look at. But, lo and behold, it did produce 1035. You can check my work if you want to. But all right, I decided to get even more creative. Once again, this is not necessary. But look at this, I created, all right, I'm going to move on past this. I think I started having too much fun with this. But I said, okay, let's go from this 0, 0 to 1, 9, then 1, 9 to 3, 9. All right, I have to admit this is probably a little ridiculous here, but I don't know. It's kind of fun. So this first one's just going to be slope of 9. So it's y equals 9x, so it's t comma 9t. And then going across from here for C2, y would be 9. And since it's moving to the right, that's positive t. And if you go from 1 to 3 for t here, there's no number that needs to be added to it or anything. So these are your two parameterizations. Yeah, so okay, once again, I took something we already had done and I decided to expand on it. So I think I won't waste a lot of time on this. But if you want to look at it, and you can always ask me about it. But it's the same thing. I'm just doing two paths, and I have to add them together. So once again, I'm substituting into the vector field. Everything's the same as before. Dotting them with the r primes. Here are the two values. So you see I have this integral, 25t to the fourth from 0 to 1, plus 1215t squared from 1 to 3. Yada, yada, yada. Look what it yielded. 10,935. And let's hope I stopped there and did not get any crazier there. Okay, it looks safe now. All right, just going to take out. Let's see. Oh. Now we're going to look at a theorem called the fundamental theorem of line integrals. And it does sort of work like the fundamental theorem of calculus in Cal 1. It's like that, just the sort of the vector field version of it instead of regular functions. Okie doke. Now this does expand for space also too, so I don't know why the definition did not include space vectors in there, but that's all right. Because it does work. It's just obviously you have to check conservative a different way. Remember, for the space, if it's a space vector, you have to do the curl thing. So this says if you have a conservative vector field. And remember, from that previous section, the first earlier sections of the vector fields, if you have a conservative vector field, that means you have a potential function lowercase f. In other words, because the potential function, when you take the gradient of that potential function, that's what gives you the vector field. So what this is saying is essentially, when and I'm trying to relate this to the fundamental theorem of just integrals in general, that little f is sort of an antiderivative of big F, as you may call it. We can call it that, sort of. It's like an antiderivative. So you're essentially taking this antiderivative, and then you're converting these to points values. Whatever the t's are, we then convert them to an x and a y, or an x, a y, and a z. And then you subtract the upper minus the lower. So it's like finding the antiderivative, plugging in the upper value minus the lower value. All right. That might have sounded a little confusing, but I think when you see it in action here, it won't be so bad. Just kind of a different way to do it. It's not bad. I'm not sure if it's necessary, any better than just using the regular f.dr, but I guess it depends on some problems. It could be better. So, okay, now I'm showing it for that last example, so now you can kind of compare. Except, of course, this one we won't be doing it 10 different ways because you only do the fundamental theorem of line integrals one way. That's because we're not worrying about R here. We don't need parameterization, in other words. No R of t is required. We just need these 2 points right here. So I want to get that potential function. So I integrate the first component with respect to x. So x squared will be x cubed over 3. 3 goes into 15 5 times. So I have 5x cubed y squared. And then for this one, the antiderivative of y with respect to y for the second one, y squared over 2 makes that 5x cubed y squared. And you may recall we're always going to get one thing in common there, and you only have to include it once. And had there been any other loose pieces, then we would have included those with it. So if you feel comfortable with that, you can move on. But if you want to check it by taking the gradient of this, the x partial and the y partial, and make sure it equals your vector field, you can do that if you want. Might not be a bad idea, but I did it here and then took the gradient, and yes, it was equal to that f, the big F. So the gradient of little f, the potential function, equals big F, the vector field. So that means, so notice we're not doing any f.dr. So now all we do is we take this potential function. Now, the fundamental theorem of calculus is obviously, because we have y as a function of x, is only one number. But here, we plug in 2 numbers, the point 39 and the point 0, 0. So you plug in 39, the 0, 0 will produce 0. 5 times 3 cubed times 9 squared, look at that answer. 10, 9, 3, 5. How about that? That yielded the same answer as we got before. So that's pretty slick. That's a lot of fun. Let's try that out again. All right. Okay, here I'm sort of telling you that in other words, when it says use any problem that ever says use the fundamental theorem of line integrals, you can assume it's conservative. You can check if you want to, but it has to be. In other words, they're telling you to use that theorem. It has to be conservative. So let's look at this. Now it's telling you the circular path it's taking, but we don't care about that at all. All we care about is we're going from 15.8 to 3.8. So we don't have to come up with any kind of parameterization for this mess right here. That's good. Numbers are kind of weird here, but that's what calculators are for. So we're going to take these 2 components and we're going to integrate them with respect to x and y, and then they should it will yield a potential function. In other words, I didn't check that it was conservative this time. I just, like I said, because it's telling us to use that theorem, it has to be. So I brought this bottom part up, and it's just a U substitution. We got to adjust for the 2 here. I didn't actually show it, but there's a 2 here. Well, the 2x can represent all that anyway. Or if I pulled the 2 out, I would have had a 1/2 from here, and 2 would have killed 1/2. So all we have is u to the negative 2 du, negative u to the negative 1. So I have negative 1 over x squared plus y squared. And the same thing here when you integrate this one with respect to y. Same result. So obviously that's our potential function. F of xy equals negative 1 over x squared plus y squared. We don't really need to include any kind of plus c there or anything, especially since we're evaluating this as a definite integral. So we're saying this fundamental theorem of line integrals is representing the f dot dr. So in other words, f dot dr, which we're not really evaluating as f dot dr, we're doing it by this theorem. So this theorem says, okay, take that potential function you found, plug in, because it went from 15.8 to 3.8. So that's the finishing point, 3.8. The starting point's 15.8. So it specifically has to tell you where it's going, from what point to the second, to where the finishing point. So the finishing point's always on top. And you can just kind of put that in the calculator. But you put in the 3.8 as the upper right there, you'll get 73. You put in 15.8, you get 289. And you can kind of math frac that in the calculator if you don't feel like getting the common denominators. But it comes out to be negative 216 over 21,097, which is the answer I have checked right there for A. All right, fundamental theorem of line integrals. I think that's a lot of fun. I guess as long as the integral's not too rude. Yeah, here's one I told you it does apply for 3 variables also, even though the theorem didn't, should have said that in the theorem. But it does work for 3. All right, well, once again, saying fundamental of line integrals makes it conservative. Saying, telling you to use that theorem. So I wrote the curl formula down here and I worked out the curl. I'm not going to walk through the steps on the curl. We've done that. I've done that in another video. But anyway, it's not too hard to follow with that formula. And don't forget to include these negatives. This is kind of tricky though because, that negative distributes through there, so it's negative 4y plus 20z right there. Anyway, so the curl was 0, 0, 0, but I knew that because it was telling us to use that theorem. So we have to get the potential function. So we integrate the m with respect to x. So the antiderivative of 6x dx would be 3x squared. The middle one, the antiderivative of negative 4z dy would be negative 4yz. And the antiderivative of this last one, you see I distributed the negative through here to make it negative 4y plus 20z. With respect to z, gives you negative 4yz plus 10z. Now you may recall when I did these before for 3 variables, that I said, if you get, obviously if they all 3 of them share a common term, we include that once. But even if any 2 of them share a common term, that goes in there once. So you see these 2 both have a minus 4yz. So that goes in there once. We have a loose 3x squared here, so we include that. And then we have a loose 10z squared there, so we include that. And, I just sort of, maybe looked at it and did it in my head. Obviously, I didn't show the work. But obviously, yeah, feel free to check this yourself. But I said that the gradient of the little f right here that I got, and it doesn't hurt to check it yourself, but I'm not going to do it right now, does equal big F. So evidently, I must have done it like in class and just said it verbally. We probably read them out term by term. Or I didn't do it. Maybe I just said it was so. But I probably checked it once somewhere. Anyway, now all we have to do is take this potential function, which is the antiderivative, so to speak, plug in this upper point. Let's go back up here. Let me show you those. Forgot to mention that, but there it is. We're going from 0, 0, 0 to 3, 4, 0. So 3, 4, 0 is the upper, 0, 0, 0 is the lower. Well, 0, 0, 0 makes this problem kind of easy. And because this makes the bottom part 0. So you put the 3 and the 4 up here for and 0 for z. Put in 3 for x, 4 for y. Oh, you get a 0 here because these are both z's. So there's no, so right there is it. 3 times 3 squared. 3 times 9, 27 is the answer. So I said, let's try this in differential form. So like I say, had we done this the other way? So I would have parameterized a line segment, because obviously I can take any path I want, but a straight line would be the easiest path. So we're kind of going way back to the first chapter. And I've done this on another problem in this chapter, but how we create parametric equations of a line, that's real easy. I mean, we know that so we subtract 3 minus 0 is 3, 4 minus 0 is 4, 0 minus 0 is 0. So we have these. I didn't write t there because 0t is just, 0. So my starting point is 0, 0, 0. So there's nothing here for those. All those are 0. So literally the right part of this is going to be the parameterization. 3t, 4t, 0. And here's dx, dy, dz. The three derivatives would be 3, 4, 0. And t would go from 0 to 1. You could check that pretty easily. 0, and you put 1 in here, you'll get 3, 4, 0 right there. Anytime you're going on a line path from a point to a point, when you come up with these parameterizations, it's going to be from 0 to 1. You would have to do something really weird to not make it be 0 to 1. So now we start substituting into here. So x is 3t, so it's 6 times 3t times dx, which is 3 dt. I guess one thing I could have written here that I didn't, maybe to be more formal, I'll just go ahead and say it verbally though, but technically I should have said 3 dt, 4 dt, but I'm sure you're not having any problem understanding that those are there. So, but I guess I should have said dx actually equals 3 dt. So please forgive me for that faux pas. Here I got minus 4, and the z makes that 0. You got it over here. Oh, this was 0 right there, and then I move over here, and I've got 0 again. So let's make sure I got that. So that's a 0, but I should have had, because this dz here is 0. So it wipes out all this. Yeah, right there. Okay. And then this was going to be 0 because of the z, not the dy. Yeah, the dy is still 4 dt, but the 0 for the z wipes all that out. So you're just left with this. So it's the antiderivative of 54t dt, which is 27t squared. 0 to 1 makes it 27, which is the answer we got right up here. So I guess technically, even if it tells you to do the fundamental theorem of line integrals, you don't have to. I would, but that's just guaranteeing you it's conservative. Although that wasn't too bad doing it this way, but I think it was a little easier. But you're entitled to your own opinion on that. But all right, this is kind of restating something we've already talked about here. Not sure why this theorem came back up again, because it seems to be the same thing we learned at the very beginning of the section, that the line integral is independent of path if and only if f is conservative. So meaning the argument works both ways. If it's independent of path, we know it's conservative. If it's conservative, then we know it's independent of path. So yeah, that sort of seemed a little weird that they put that theorem in there, because that, to me, that seems exactly the same as what I put back up here at the very beginning. So here's a trig one. That's always fun. So my, the derivative of this respect to y, cos x, cos y. nx, would be cos x, cos y. So that's that means it's conservative. So the fundamental theorem of line integrals applies. Now we integrate the first term with respect to x. So the antiderivative of cos of x dx would be sine of x. So we have sine x, sine y here. The second term I integrate with respect to y. So I have sine x, sine y. So they share a common term. So that's going to be the potential function. So the potential function is sine x, sine y. And all we have to do is plug in this upper value right here minus that lower value. And we get, so sine x, sine y, put in the upper value. Sine of 3 pi over 2 is negative 1. Pi over 2 is positive 1. Multiply those together, you get negative 1. And of course, sine of 0 is 0, so it makes that 0. Sine of negative pi is 0, but once you have that first 0, wipes that out. So we have negative 1 minus 0 equals negative 1. And that concludes this video on conservative vector fields and independence of path.